So in the previous class, we have seen that the solid state laser suffers from poor capability of heat dissipation, basically because its surface area to volume ratio is very small. If you try to increase the output power of the laser by dumping more input power, then it invariably results in poor heat dissipation, which can increase the thermal stress as well as mechanical stress, which can damage the glass rod and also results in thermal lensing effect. The one exception of the solid state laser is the fiber laser, which makes use of the similar gain medium as that of a conventional solid state laser, but here the lasing originates from a similarly dropped glass, but in the form of a fine strand several micron to millimeter in diameter and several meter to even up to many kilometers long. This thin and long geometry readily offers a remarkably high surface area to volume ratio, and thus the fiber laser have inbuilt capability of heat dissipation, of rapid heat dissipation to the surrounding. So let us take a typical example. For example, let us consider a typical solid state laser, say of diameter 2 centimeter and length say 10 centimeter, very typical. So its volume is pi into 1 centimeter square into length is 10 centimeter. So this many cc. So equal to 10 pi cc. And let us consider a fiber which has the same volume as that of this solid state laser, but its diameter is say 2 millimeter instead of 2 centimeter. Its diameter is 2 millimeter, and let us find out its length. That would give the same volume. So its volume also would be 10 pi cc. Its diameter is 2 mm, so its radius is 1 mm. Therefore 1 by 10 square into its L, that we will have to determine. So L becomes pi is cancelled, so 100 into 10, 1000 centimeter. So its length becomes 1000 centimeter to give the same volume as that of this rod, laser rod, which is 2 centimeter of diameter and 10 centimeter of length. Now let us see what is how the surface areas of these two systems compares. So what is the surface area of this rod? It is 2 into pi into r. R is 1 centimeter into length. Length is 10. So this many centimeters square. This is equal to 20 pi centimeters square. And what will be the surface area of this fiber, whose diameter is 2 millimeter and length is 1000 centimeter? This is 2 pi into r. R is 1 millimeter, that is 1 by 10 centimeter, into length is 1000 centimeters. So this many centimeters square. So this is equal to 200 pi centimeters square. So you see, its surface area is 20 pi centimeters square, and this is 200 pi centimeters square. So although their volume is same, but this has a surface area which is 10 times more than the surface area of this. So that means if you take a linear proportionality, you can dump 10 times more power into this, and yet the situation, that is the heat dissipation capability of this, would ensure that you can extract 10 times more output power from this laser without damaging it, without causing any thermal damage to this system, simply because the surface area of this is now 10 times more than this. So its heat dissipation capability is 10 times better than this. So this is the underlying physics. So the thin and long geometry readily offers a remarkably high surface to volume ratio, and thus the fiber laser have inbuilt capability of rapid dissipation of heat to the surroundings. The fiber laser was invented in 1961. Within a year of the invention of the laser, that was in 1960, by an American scientist, Elias Snyder, when he optically pumped a strand of glass fiber by wrapping it around a flash lamp. So basically what he did, he used a flash lamp, flash lamp, and wrapped the fiber, that is the glass strand, around it. So as the flash lamp emits light, it will actually enters this fiber through its site. However, extremely inefficient pumping of a fiber through this enormously large lateral surface area, its surface area is extremely high because deliberately we have increased the surface area to increase its heat dissipation capability. But this poses a problem because it becomes site pumping very inefficient because its surface area is so enormously large. However, this extremely inefficient pumping of a fiber through this enormously large lateral surface area did not allow the exploitation of its heat dissipation capability. Because pumping itself is so poor that hardly there has been any heat dissipation. So that capability, that it has such large surface area which gives much better heat dissipation capability, cannot be exploited, could not be exploited. So its performance was very poor. Now this limitation essentially halted any meaningful progress in the research and development of fiber lasers for almost 3 decades. That is from 1960 almost up to 1990, there was hardly any progress in the fiber laser performance. There was hardly any activity also, because the main problem was as to how pump the fiber from its site. It became very inefficient pumping of the fiber because of its exceptionally high, large surface area. That is required to increase its heat dissipation capability, but then it comes in the way of pumping if you have to pump it by the site itself, by its lateral surface. However, fiber lasers had their second birth in 1990s once heterostructured diode laser technology matured enough to allow the end pumping of a fiber. Say heterostructured diode laser is basically semiconductor laser. It is called either a diode laser or a semiconductor laser. Heterostructured diode laser is allowed operation of a diode laser for the first time in a continuous mode. We will of course understand more about this heterostructured laser when we take up the working of semiconductor laser, just following our study with fiber laser. Now this laser, which gives a very narrow beam of light, this semiconductor laser, can be used to pump a fiber through its end. Instead of pumping from its side, which is very inefficient because of extremely large surface area that it presents, the semiconductor laser allowed pumping this fiber from its end. So you introduce the pump beam from its end. Although the end is its aperture is extremely tiny, but the very narrow output achievable from a semiconductor laser allowed the pumping even through this narrow bore of the fiber, end pumping. And as a result, the optical fiber laser took its 7-second mark around the time when such a semiconductor laser was available. Now, around that time, a British physicist, David Payne, and his co-workers at Southampton University invented a fiber-based light amplifier. So long we were discussing about fiber laser, but now this David Payne and his co-workers also invented a fiber-based light amplifier. That means a fiber can also amplify light. Just as it can operate as a laser, it can also perform the low role of light amplifier. This was a very significant achievement because of this. You see, the capability of such an amplifier, this fiber amplifier, to directly boost the greatly weakened optical signal that has traveled through a long distance of optical fiber without requiring it to be converted first into electrical signal, brought a revolution in fiber optics communication and internet connectivity. Well, let me elaborate it a little. You see, today the semiconductor laser integrated with optical fiber is the backbone of long distance global communication. The fiber has been laid under the sea, under the ocean, and underground for thousands and thousands of kilometers. That is required if you have to communicate crisscrossing the world, across the world. Global communication is based on such fibers, which are running under the sea, ocean, and of course under the ground. As a matter of fact, let me tell you that today the total length of fiber that has been laid under the sea, under the ocean, under the ground exceeds 3.3 times the distance between Earth and Sun. Such is the power and dominance of optical fiber today. So, how does this finding of Payne impacted this? Well, you see, let us consider a long distance communication through a fiber which is 10,000 kilometers long. Not surprising, there are such fibers which has been laid, say, under Pacific or Atlantic. So this is, say, 10,000 kilometers long. And in one end, we introduce the emission from a semiconductor laser, which carries the data stream that has to be transmitted from this end of the fiber to its other end, which is say 10,000 kilometers or even longer than that in length. So the laser beam enters the fiber from this end, which carries the data stream, of course. Now, although the wavelength of the semiconductor laser and the fiber material is so chosen that there is hardly any absorption of the light at this wavelength into this fiber material. Yet we say that this absorption is very, very insignificant. But however small, it is not zero. It has some finite value. Therefore, as it travels through hundreds of kilometers, the signal actually weakens. And then after traversing a length of a few hundreds of kilometers, it becomes too weak to carry the information any further. Therefore, the signal needs to be boosted. Say at every 100 or so kilometer, the signal is boosted. So this is booster. Before this discovery of pain, how the signal boosting is to take place? This optical light, this light which has become weakened as a result of absorption, it will be converted, light will be converted into electrical signal. And then this electrical signal will be amplified very easily in electronic amplifier, very standard. So this is then amplified. And after amplification, it is then converted back into light. And then this light would then travel to the next stage. So this boosters basically is light to electric to light converter. And for such a long distance communication, there will be multiple such boosters, many boosters. And this made the communication system very complex and cumbersome because of this light to electric to light conversion that was essential. However, the discovery by Payne that light can be amplified as light through optical fiber changed the scenario. It was indeed a game changer. So then what happens now? So this weak signal, so this is the fiber. At this point, you put this light amplifier. So it will travel through the optical fiber, which will perform as an amplifier. So this fiber, the light goes into this, at the other end, you have the amplified light goes through the next stage of fiber. Then you have again light amplification. And this light amplification, it can amplify the light to such a great extent that the booster stage, the interval, the length for which boosting was required increased from about 100 kilometers to 500 kilometers. That means the number of these booster stages also reduced. Not only it became a all light fiber optics communication, there is no need to light to electric to light conversion. Further, the number of these stages also reduced, almost 5 times reduction. So this all light fiber optics communication without the requirement of any intermediate conversion of light into electronic form and back to light again after amplification has profoundly impacted the area of communication. So you now know that this invention by David Payne, this co-author of fiber amplifier, how it has impacted the communication that we utilize today, fiber-based communication. Then further, thanks to the pioneering work of British American scientist Charles Cow, today we have optical fibers through which light packed with digital data can travel with practically no loss. Nicknamed as father of fiber optics communication, Charles Cow won the 2009 Physics Nobel Prize for his pioneering work that laid the foundation for the development of nearly lossless fiber that exists today. And ready scalability of the power of the fiber laser that has reached today tens of kilowatt in CW operation and megawatt in pulsed mode was primarily to this, because this fiber hardly absorbs any light. Therefore, the power of the fiber laser can be greatly enhanced as it suffers hardly any absorption from the incident light. It hardly absorbs any of the incident light. The credit, of course, goes to Charles Cow. We shall study here at an elementary level the mechanism of pumping and working of a fiber laser. So, how does a fiber laser is pumped and how does it work? So, the ability of an optical fiber to keep the light confined within its core and a large acceptance angle for the entry of the light through its ends are the key to the emergence of fiber lasers as the leader in industrial, medical, and directed energy application. An optical fiber acquires these abilities by exploiting, as you know, the property of total internal reflection of light. We have already studied this when we spent some time in understanding behavior of light, but let me once again refresh your memory by taking another look at total internal reflection. You see, three situations have been depicted here. Three situations. But before we get into this, you know that when light travels from a denser to rarer medium, light travels from a denser to a rarer medium, then it undergoes refraction and bends away from the normal. This is the normal. So this property is actually exploited. How do you do that? You know that when light falls on an interface, a part of light is reflected back into the incident medium, and rest of the light is refracted into the second medium. Now, for a wide range of angle of incidence, this is what happens. Part of light is reflected back into the incident medium and rest is refracted into the second medium. However, when this angle of incidence assumes a particular value, which we call theta c, then the refracted ray grazes over the interface. That means the angle of incidence now becomes 90 degree. So what happens then? If now the angle of incidence just exceeds this angle is called critical angle, at which the refracted ray grazes the interface. If the angle of incidence just exceeds this angle of this critical angle, theta c, then there is no more scope for the refraction to occur, because refraction has already assumed the highest value, which is 90 degree. Therefore, the entire light is now reflected back into the incident medium. And quite aptly, this phenomena is termed as total internal reflection of light. So, how can this phenomena be harnessed to bend light at will along the surface of a fiber, facilitating its journey from one end of the fiber to the other without any spillage, that is, without any loss of energy through refraction? The answer lies in cladding the fiber with a material of refractive index lower than that of the fiber itself. So basically, you take advantage of this. You do not allow, if the light travels from denser to rarer medium, and if the angle of incidence exceeds critical angle, there cannot be any refraction of light. So no loss of energy due to refraction. So for this, you actually, this is your core, that is the glass core, and you put a cladding whose refractive index is less than that of the core. So if you launch a ray of light on this interface, core to clad interface, at an angle which is more than the critical angle, then there cannot be any refraction of light. No light will pass, travel, or can get into the core. An entire light will be reflected. And after reflection, as it hits the other core clad interface, it will again be incident at an angle exceeding the critical angle. So it will undergo this total internal reflection every time it hits the clad and core interface. Therefore, this beam of light will travel down the fiber through such zigzag paths by undergoing reflection at every time it interacts with the clad and core and clad interface, and would reach the other end without any loss of energy, spillage of energy through refraction. This concept was first conceived and demonstrated by Harold Hopkins and his Indian student Narendra Singh Kapani in 1950 at Imperial College in London. Kapani is also credited with coining the word optical fiber. It may be of interest to note here that Kapani was posthumously honored with India's second highest civilian award, the Padma Bhushan Award, in 2021, the year of his death. Well, I will end here today, and in the next class, we'll begin right from here, and we'll see how actually this property can be utilized to operate largely in fiber laser, and how it has the capability, it gives it capability to extract extremely high power from the operation of such a laser.